Okay, so let's start. Um, in the last few classes, we studied what a proper cone is, what generalized inequalities with respect to proper cones are, and what is the dual cone for a given cone. Right. Along the way, we saw a few examples and one application. The application was uh, trying to maximize multiple functions of a given set of variables. Like when you have multi-objective optimization, you may want to minimize, let's say, multiple functions which could be conflicting with each other. But in this case, you may or may not be able to find a minimum. The minimum may not be well defined, but definitely the set of minimal elements is well defined. And in this case, it makes sense to talk about the minimization problem is one of finding a minimal point, any minimal point. All right. Now, there's another use for generalized inequalities in the sense of defining convexity itself. Right. So, if you recall, what is a convex function? We say that a function is convex if f of alpha x or f of alpha x1 plus 1 minus alpha x2 is less than or equal to alpha f of x1 plus 1 minus alpha f of x2. Right. So this was the definition of convexity for any function f defined over some vector space but takes real values. Correct. Now, in general, I could consider more general functions. For example, f from V to Rm. It could be a function from Rn to Rm. Okay. Now, in this case, the standard inequality doesn't make any sense. So the question is, how do we define convexity? Right. So we can use generalized inequalities. So with respect to some generalized inequality k, we say that f is convex. So we have some proper cone k, which is maybe defined over Rm. One way to think about it is just think about the component-wise inequality. So with respect to this generalized inequality, we say that f is convex if f of alpha x1 plus 1 minus alpha x2 is less than or equal to, with respect to this generalized inequality, alpha f of x1 plus 1 minus alpha f of x2. Okay. So for example, suppose that f is a composition of m functions, right? So f of x, let's say that it is a function from Rn to Rm, right? You can write this as f1 of x, f2 of x up to fm of x, right? Now, when would this function be convex with respect to the component-wise inequality? Yeah? Correct. Or what can you say about the individual functions f1, f2? Yeah. So basically, this would be convex with respect to the component-wise inequality if each of the f1, f2 up to fm are all individually convex. So there are many such scenarios. This is one example with respect to one generalized inequality. But the point that I'm trying to make here is that many of these results, many of these techniques can be generalized a lot. Okay, so in many cases we'll be restricting ourselves to certain examples, certain cases, but these tools are extremely powerful. It all depends on how. So it makes sense to find out what the limitations of these mathematical tools are and how general these tools are. We won't be talking too much about these convexity with respect to generalized inequalities, but it is something good to know. Right? That you can even handle convex optimization problems where the goal is it's in fact something like a multi-objective optimization where, let's say, each of these functions is convex. Okay. So going back to what we saw in the previous class, we defined what a dual cone is, right? In today's class, we'll wrap up our discussion on convex sets, and I'll try to give sort of the way forward. What our goal is. Recall that our goal is to solve convex optimization problems or come up with algorithms or techniques or approaches to solve convex optimization problems, constrained convex optimization problems. If there are no constraints and the function is smooth, then we've already seen a bunch of different techniques that we could use to numerically solve convex optimization problems, right? But we still don't know how to handle convex problems where we have constraints. Okay. So in hopefully in today's class, I'll be able to cover that, and we'll see how a general approach that can be used to solve constrained convex optimization problems. We won't see why that works. Okay, we'll see a technique, and then we'll spend a good portion of the course seeing why this particular approach will work. Okay, but before that, I'd like to discuss two last topics with respect to convex sets. Okay, so one, we're going to revisit hyperplanes. So how do you define a hyperplane? Yeah, so in general, so a hyperplane in Rn is basically the set of all x such that A transpose x is equal to some b, or in general, the inner product between some vector A and x is equal to some b. Okay, so this defines a hyperplane. This could easily generalize to cases where you're not even dealing with Rn. Okay, as long as you have an inner product, this definition makes sense. All right. So suppose I give you two sets, two non-intersecting sets. Okay, and I want to separate these sets. For example, one classical application is that of classification. So basically, you randomly sample points from two sets. You don't know whether they come from set A or set B. The question is it possible to design a classifier that tells you whether a given point belongs to set A or belongs to set B? So what could be the case? For example, I have some set A and I am given some other set B. Right? So I want to know if it is possible to design a simple classifier or a simple function which distinguishes whether a given point belongs to set A or set B. And what is the simplest function I can think of? A linear classifier. So what I want to know is it possible to construct an A and B such that x belongs to A implies the inner product between A and x is, let's say, greater than or equal to B, and x lies in B implies that the inner product between A and x is less than B. Okay. So if something like this exists, then this is called a separating hyperplane. So if it is possible to have such an A and B, then the following set, the hyperplane, is called a separating hyperplane. So if I give you two arbitrary sets, is it always possible to construct a separating hyperplane? Right? No, suppose A and B are disjoint. Okay. I give you two arbitrary sets A and B, both of them being disjoint. Is it always possible to construct a separating hyperplane? Sure, true. So for example, if I have, this is my set A and my set B looks something like this. Right? This is a visual example of a case where it's not possible to draw a line that separates A and B. Right? So these two are not linearly separable. But it's possible to give sort of a sufficient condition under which A and B are linearly separable. And that example and that condition is simply if A and B are both convex and disjoint, then there always exists a separating hyperplane. I won't prove this particular result, but if you're interested, you can just take a look at the textbook by Boyd and Vandenberg that has a complete proof. Okay. But what I'm more interested in are not separating hyperplanes, but what are called supporting hyperplanes. And this is sort of the natural generalization of a tangent. Right? So you can think of this as the tangent plane to a given set. So suppose I have a set A. Right? I say that a hyperplane, or how do you define the tangent at this particular point? So this, I say that a hyperplane is a supporting hyperplane if the hyperplane passes through a point on the boundary, but at the same time the entire set is contained on one side of the hyperplane. Okay, so let me define supporting what is a supporting hyperplane. So take any some x naught that belongs to the boundary of the set A. Okay, so if, let's say, A transpose X, or the inner product between A and X is, let's say, greater than or equal to B for all X, or the following way, A comma X naught for all x belongs to A. Then the set of all, let me call this y such that so this is supporting hyperplane. Exactly. So I'll come to that. So in general, a supporting hyperplane may or may not exist for a given set. Now, even if the set is non-convex, it's possible that at some points you can construct a supporting hyperplane. But if it is not convex, so for example, if you have some function, some set that looks like this is my set A, right? At this point, for instance, I will not be able to construct a supporting hyperplane. Okay. But at any of these points, I would be able to construct a supporting hyperplane. On the other hand, if the set A is convex, then at every point on the boundary, I can in fact construct a supporting hyperplane. True. Yes, you will be able to construct a supporting. That's because the convex hull is convex, and every point on that boundary is going to have supporting hyperplane. So at any point that lies both in the boundary of A and on the boundary of the convex hull of A, you will be able to construct a supporting hyperplane. Okay, but also you have to be a little bit careful, because it may be possible that you can, even if the set is non-convex, you can construct a supporting hyperplane at every point on the boundary of A. And why can that happen? Note that, let's look at the requirement. We want the inner product between A and X to be greater than or equal to the inner product between A and X naught. Correct? Now suppose that the set A is not convex, but actually lies in a lower dimensional subspace. For instance, let's think about R3. Correct? So in R3, suppose I have a non-convex function, a non-convex set that lies within a plane. Okay, so this in fact lies inside a hyperplane. Correct? And this condition is trivially satisfied because it lies in the hyperplane, right? So you'll have the A transpose X equal to A transpose X naught for every X naught in the set. So in this case, this condition is automatically satisfied. But on the other hand, if we are considering, let's say, solid sets, then or the affine hull does not is or the affine dimension is equal to the dimension of the entire space, is equal to n. In that case, this kind of a definition would probably be more useful. Correct? But nevertheless, if the set A is convex, then you will always be able to construct a supporting hyperplane at every point on the boundary. How would we prove this? That we will not prove that at all, right? That's a different thing. But suppose I were to use what we've already seen. Let's assume that the separating hyperplane theorem is given to us. Correct. So what would be the two sets? After all, I need two sets to use the separating hyperplane theorem, two convex sets. Yeah. What do you mean the reflection about any hyperplane?
Choose a hyperplane. The convex set.
Which one? A is a convex set in Rn. Okay. So I want to show that at every point on the boundary of A, I can construct a supporting hyperplane that passes through that particular point.
So for every point,
Correct.
choose a hyperplane.
Okay.
For which we can reflect that.
What do you mean by reflect that point?
Take the reflection of that point with respect to the hyperplane.
Okay.
So that hyperplane is a separate hyperplane, but those two convex sets.
Okay, so let's do that slowly. So suppose I give you a convex set A. Okay. So I'm given this particular point. Okay. We're considering any hyperplane that passes through this point.
That doesn't intersect. That's
So you mean to say any hyperplane? Okay.
let that set.
Okay.
About that hyperplane.
Okay. So I get this reflection, which looks something like this. Let me call this A prime.
Separate hyperplanes for those two sets.
True.
The hyperplane will have some minimum distance from the set.
Okay.
The given set. You can move it closer and closer until that limit tends to 0 basically. That then becomes a supporting hyperplane. And then you can do that with everything.
You have to be a little careful. I want to show that I want to construct a supporting hyperplane at this particular point. So this is my x naught. Okay. Let's suppose that I want to do what you say. And I construct the following hyperplane. Okay. Now, if I reflect, I get something else, right? But then no matter how close I move to it, if I want this hyperplane to pass through this point x naught, it will not be a supporting.
That will also have corresponding point which is that minimum distance from that.
Which one?
The hyperplane you've chosen.
Correct.
There will be a set in that set. There will be a point in that set which will be at the minimum distance from.
Okay. Correct.
So you can get the supporting hyperplane for that point.
Okay, but that would be a supporting hyperplane at that particular point. So all you've shown is that there exists a supporting hyperplane for some point on the boundary, not for every point. Correct? But there's a simpler approach. Correct. So you take the point x naught. So essentially, you just take, let's say I take A equal to, maybe I just want to take the relative interior of, we call this A prime, interior of A, and my B prime to be equal to just the set containing x naught. Okay, these two are non-intersecting sets. Right? So, and both of them are convex. Right? The relative interior is also convex. this just contains a single point, so obviously it is convex. So there exists a separating hyperplane that separates A prime and B prime. But then every point in the relative interior lies on one side. So even if I include the boundary, it will still be on one side of the hyperplane. Right? So which means that the separating hyperplane would be the supporting hyperplane for this particular set, and it would pass through x naught. Now, of course, if A is a lower dimensional set, then I don't need to go through anything. I don't even need this particular theorem. All I need this for is if the, let's say, the interior is non-empty. Right. So that's a way to just prove this particular theorem. Okay. But the supporting hyperplane also gives you some geometric information. So for example, suppose I give you a polytope. How would I characterize a vertex of this particular polytope? So consider, let's think of R2, right? A polytope in R2. So you know that so this is a convex polytope. So every point on the boundary, at every point on the boundary, I can essentially draw a tangent such that the entire set is on one side of this tangent line, right? Now, what distinguishes in terms of this supporting tangent or supporting hyperplane, what would distinguish a vertex from a face or an edge? Correct. So if I take any point on the edge which is not a vertex, how many, of course, so I construct any tangent at this particular point. How many points of A does this tangent contain? Infinitely many points. Right? But on the other hand, if I take any vertex, then it is possible to construct a tangent which passes through exactly one point of A. So that's a way of defining the vertex of a given polytope. Right? So even if you generalize this to higher dimensions, a point is said to be a vertex if there exists a supporting hyperplane at that particular point, which passes through exactly one point of A, which is that particular point, x naught. It doesn't mean that every supporting hyperplane contains exactly one point. It means that it is possible to construct a supporting hyperplane that contains exactly one point of A. Correct. So then it doesn't make sense to talk about the vertex of a circle, right? Now, if these are only for this, of course, assuming that this is a polytope. In general, it's possible to construct supporting hyperplanes that pass through exactly one point. if it's not polyhedral. The circle is the example, is a good example. But this particular result, right, that if A is convex, then every point on the boundary has a supporting hyperplane, correct? So now if I take the intersection of the half spaces formed by these supporting hyperplanes, then what do I get? Yeah, I get a convex set, but which set in particular? So suppose I take this particular A, right? Think of this particular A. For every point on the boundary, I have a supporting hyperplane. So for this supporting hyperplane, I consider this half space, the half space that contains A, right? Now there are infinitely many points on this boundary, and at each point I have a supporting hyperplane and the corresponding half space that contains A. Now let us say I take the intersection of all of these half spaces, these infinitely many half spaces. What would I get? You'd get back A, right? So this is one way to sort of justify the statement that I made a long time ago, that every convex set can be expressed as an intersection of half spaces, potentially infinitely many half spaces. You simply take the intersection of all of these half spaces defined by the supporting hyperplanes. Now, of course, this works only if the interior is non-empty. This is what I said. That's one point. The other point is I'm also implicitly assuming that the set is closed, right? Because the intersection of these half spaces would give me a closed set. Okay, so any closed convex set can be written as an intersection of potentially infinitely many half spaces. Which is not necessarily true if the set is not convex. In fact, it is not possible if the set is not convex, because if you take any so a half space is a convex set, and intersection of arbitrarily many convex sets will always give you a convex set. Any questions so far? I'm sorry?
There's a convex set. You took x naught out of that.
You took x naught out of?
So it's A slash.
Okay, so you're removing x naught from the interior of A or the boundary of A? Okay.
Either x naught is a part of A.
Correct. It could be anywhere in A.
Yeah.
Okay.
So it sits on with respect to where it is. Now, once I remove it, the set is not one.
Correct.
If it is on the boundary,
Yes.
can the hyperplane still be constructed such that the set becomes convex? Or is it nothing? Can I draw a hyperplane at the point from where x is removed?
Okay.
And I say the relative interior of the new set formed is one.
So one thing is A need not be one thing I try to clarify is that A need not be a closed set, and therefore the boundary of A may or may not be in A. Right? If you recall the definition of the boundary, how did we define the boundary? You consider the closure of A and you remove the relative interior. Correct? So the closure of A may or may not be equal to A itself. Right? So even if I remove a point on the boundary of A, if I the boundary of A will still include that particular point. So it will always be possible to construct a supporting hyperplane at that particular point. Okay. So x0 is a point on the boundary which may or may not be in A. But of course, if I remove a point from inside of A, from the interior, the set will no longer be convex, but it's still possible to construct a supporting, right, at every point on the boundary. Okay, any questions so far? Okay, so we'll now do a bit of a context switch. We'll move to a slightly different topic, which is how do we solve convex optimization problems, right? Or so in order to study this, um, we'll look at the class of problems, convex or not, which can be expressed in the following form. So consider any optimization problem of the form you want to minimize some function f0 of x subject to the constraints that let's say fi of x is less than or equal to 0 for I equal to 1, 2, 3 up to m. So there are m inequality constraints, and you also have a bunch of equality constraints. Hi of x is equal to 0 for I equal to 1, 2, 3 up to p. Okay. In general, each of these FIs and HIs may have different domains. Okay. But we'll assume that, so the constraint set is non-empty. Okay, the domain, the intersection of all of these domains is also non-empty. Okay. The constraint set is non-empty and there exists an optimum. Okay, so there exists some point x that satisfies these constraints and therefore also minimizes f0 of x. Okay, let me call that say f star. That's equal to the minimum. The minimum is achieved at some point. Our goal is to find out how do we find this particular minimum for such a given optimization problem. Okay, so any point that satisfies these constraints is called a feasible point. Any x that satisfies This is what we call a feasible point. So we know that there exists at least one feasible point. Now I have a given optimization problem. I'm eventually going to define a new optimization problem that is kind of connected with this, but is hopefully easier to solve than this original optimization problem. Okay, so I define a new function which I call the Lagrangian. So it is a function that takes as input x, but also takes as input two vectors where lambda, so this Lagrangian is a function that takes as input x and also two real vectors lying in Rm and Rp and outputs a real number. Okay, so I'm adding some more variables. And this is basically a linear combination of the function that we wanted to minimize and each of the constraints, the functions corresponding to the constraints. So this is equal to f0 of x plus summation I equal to 1 to m lambda I fi of x plus summation j equal to 1 to p of nu I hi of x, nu j hj of x. So these two sets of variables are called dual variables. They're also called Lagrange multipliers. Okay, so I had my original problem, which was a constrained optimization problem. Now, at this point, I'm not assuming that these FIs are convex or anything. Okay, this approach is very general, but we'd see that some of these apply only when these functions are convex. Okay, but nevertheless, I can always define this Lagrangian. Okay, I've introduced these two new sets of variables, the Lagrange multipliers, and this function is well defined. Now, for this, I'll also define the Lagrange dual function, which I'll call g of lambda nu. This is going to be equal to the infimum over all possible x in the domain. Okay, so the domain is basically where all the functions are well defined. Okay, it doesn't necessarily have to be a point that satisfies all the constraints. So in general, if all of these FIs are well defined on all of Rn, then the domain would simply be Rn. Okay, so this is the intersection of the domains of all the FIs and the domains of all the HIs. So this is the infimum of the Lagrangian. Okay, so you can think of this as an unconstrained optimization. Now, firstly, I will not prove this right now, we'll see this later. The Lagrange, irrespective of whether all of these Fi's are convex or not, the Lagrange dual function will always be convex. I'm sorry, I should rephrase that. The Lagrange dual function will always be concave. So even if the F0, F1, F2, H1, H2, all of these are convex or not, this function will always be concave. The second point, which we'll see in a little bit, g of lambda comma nu, this will always be less than or equal to f star, the minimum of f, the constrained minimum of the function. So recall that f star is the optimal value for this given constrained optimization. So this will be less than or equal to f star for all lambda which are component wise greater than or equal to 0. So every lambda I is greater than or equal to 0, and for all nu in RP. Okay, so it's less than or equal to f star. Okay, so let's first see why this could possibly be true. Now we are given this particular quantity, right? So the Lagrangian is equal to this particular quantity. Now suppose that x satisfies all the constraints. Okay, so if x satisfies the constraints, then what can you say about j of x? Go back to the definition. Yeah, it would be equal to 0, correct? So if x satisfies the constraints, then hi of x should be equal to 0 for all I. And if it satisfies the constraints, then fi of x is less than or equal to 0 for all x, right? So each of these terms would be equal to 0, and if all the lambda i's are also greater than or equal to 0, then each of these terms would be less than or equal to 0. So L of x lambda nu, this would be less than or equal to f0 of x. This is true for all x that satisfies the constraints, for all lambda, and for all nu, right? Now what happens if I minimize both of these, both sides, subject to the constraints? Right? So I get g of lambda nu is less than or equal to f right? But maybe there's one more step that I've just missed out. So recall that g of lambda nu, this is equal to the minimum over all possible x, not necessarily those satisfying the constraints, right? So this is the infimum over of L of x lambda nu over all possible x in the domain, but this is less than or equal to the infimum of x lambda nu, where this infimum is only taken over the constraint set. Which is equal to f star, or which is less than or equal to f star. Okay. The domain always contains the constraint set, right? Sure. I mean, for the constraints to be satisfied, x has to be defined, right? So the domain is all the regions where all the fi's are well defined. That's it. Right? So the domain will always contain the constraint set. Okay. So now I can define the dual optimization problem. Which is, let's say since this is true for all lambda greater than or equal to 0 and for all nu, this will also be true if I maximize g with respect to lambda and nu. So I define this new optimization problem, which is to maximize over all lambda greater than or equal to 0 over all nu in Rp of g of lambda comma g. And let us say that the optimal value for this is some g star. So I had my original optimization problem, a constrained optimization problem, and now I converted that into another optimization problem with, in some sense, fewer constraints, because the only constraint is that lambda should be greater than or equal to 0, right? So this gives me some value g star, and I know for sure that g star is less than or equal to f star. So this gives me a lower bound on the actual constraint minimum. Now this property is called weak duality. In certain cases, it turns out that g star is equal to f star, and this is what is called strong duality. If strong duality holds, then essentially I could solve the dual optimization problem instead of the original optimization problem. Okay. But at the face of it, it doesn't feel like we've simplified anything. Right? I had an original optimization problem which I couldn't solve. I defined this dual optimization problem, which again I don't know if I can solve or not. But as it turns out, in many cases, the dual optimization problem is easier to solve. Sometimes you can get analytical solutions, a closed form expression for the solution. Sometimes, and in fact, most convex optimization algorithms try to solve the dual optimization problem. There are numerical techniques in order to solve for this. Okay. And in fact, we'll give a set of conditions, or in other words, a set of equations. If you can numerically solve those equations, then you will get the solution to the dual optimization problem. So if g star equal to f star, then this is called strong duality. So to get a sense of this, let's look at an example, a simple linear programming problem. Right? We'll see the primal or the original optimization problem. We'll try to construct the dual optimization problem and see what they look like and if the values match. So let's take a very simple example. Let's say I want to minimize x1 plus x2 such that, or let me take a more general, let's first take a general linear optimization problem. So I want to minimize, say, C transpose X subject to the constraints that A times X equal to B and X is greater than or equal to 0 component wise. Okay. Now, in fact, you can show that given any linear optimization problem, any linear programming problem, you can always pose it in this particular form by making suitable changes to the variables. So if you know how to solve problems of this kind, you can solve any general linear programming problem. So let's suppose that I have such a linear programming problem. What would be the dual optimization problem? So first, what would be L of x lambda nu? So here I'm assuming that A is an m by n matrix, x belongs to Rn, and that's it. So in this case, P would be equal to L. So what would this be equal to? It is f0 of x, which is C transpose x, plus, so in some sense this contains m different equality constraints, right? So summation I equal to 1 to, let me write this slightly differently. So I have P equality constraint, so this would be P cross n and m equals m. So I equal to 1 to P. Now this is Ax equal to B, or in other words, Ax minus B is equal to 0. So this is the same as x greater than or equal to 0 and Ax minus B is equal to 0. So each of these would be lambda I times AI x minus BI. Okay, yeah. That's correct. So this would be nu I times AI x minus BI, where this AI would be the ith row of the matrix A. What do you mean this specific? So that's why we are sticking to the same notation. Okay, because after all, there is a difference between the variables corresponding to the inequality constraints and those corresponding to the equality constraints, and that essentially comes from the dual optimization problem, right? So here you are maximizing over all lambda greater than or equal to 0, but there is no constraint on nu. Okay, but this nu corresponds to the equality constraints, and the lambda essentially comes from the inequality constraints. This is a component-wise inequality. Correct. So it's a component-wise inequality. So it is defined with respect to the non-negative orthant. The cone is a non-negative orthant. So in general, if I just say greater than or equal to, I implicitly mean it's just a component-wise inequality. That's it. Okay, so this plus summation I equal to 1 to n of nu I times I have xi should be less than or equal to 0 nu I times minus xi. Or I can write this in a more, sorry, this should be lambda I times minus xi. But I can write this more compactly as C transpose X plus vector nu transpose AX minus B minus lambda transpose X. Okay. If I simplify this a little bit, I basically get do it in 2 steps. C transpose minus lambda transpose plus nu transpose A times X plus minus nu transpose B. So this is equal to, just rewriting this a little bit, A transpose nu plus C minus lambda whole transpose times X minus nu transpose B. Alright. Now what will the infimum of this particular quantity be equal to? Remember, this is an unconstrained minimum. Yeah. Why? Correct. But is it always true? As long as it's a function of x. think about it a little bit. So think about it in terms of R2, right? If it is, exactly. So basically, if this term is non-zero, then the minimum would be minus infinity, because because it's a linear function, right? So there's always a direction along which you can go such that x decreases, right? Because the slope is essentially non-zero. But if this quantity is equal to 0, then it's a constant function. In this case, the minimum would be equal to this itself, right? So this would be equal to minus nu transpose B if this quantity were equal to 0, or A transpose nu plus C equal to lambda, and it's equal to minus infinity otherwise. Right? So this is g of lambda nu. Is it clear why this is equal to the minimum? Correct. Which one? So I'm taking the minimum over all possible x, right? So I want to know what is the minimum of this function over all possible x. Yes. So if this quantity is non-zero, then then basically you can take x, some of the components being plus infinity, some of the components being minus infinity, such that the overall function is equal to minus infinity, right? So what is the dual optimization problem reduced to? It is to maximize g of lambda comma mu over all lambda greater than or equal to 0 and nu in Rn, or Rp in this case. So what would that be? I claim that this is the same as maximize minus nu transpose B subject to the constraint that A transpose nu plus C equal to lambda and lambda greater than or equal to 0, right? Right. So this is always, so nu transpose B is always going to be greater than or equal to minus infinity, right? So maximizing this is the same as maximizing this subject to these constraints. Now I have two constraints over here, A transpose nu plus C equal to lambda and lambda greater than or equal to 0, but I can just replace this with a single inequality constraint because this does not contain lambda anywhere. This is the same as maximize minus nu transpose B subject to the constraint that A transpose nu plus C is greater than or equal to 0. But what sort of an optimization problem is this? Yeah. It's again another linear program. So the dual of a linear program is just another linear program. But then again, it doesn't seem like we've simplified anything, right? Our goal was to solve a linear program. I ended up with another linear program. but sometimes it can be helpful because the dimension of this particular linear program may be smaller, right? So over how many variables am I optimizing this, right? What is the dimension of this particular problem? Where does nu lie in RP, right? So, and recall that we were doing this optimization in essentially some affine space of dimension equal to P, correct? So if I'm doing so, then in general, sorry, it should be in an affine space of dimension n minus P, correct? Because Ax equal to B, I have P equality constraints. So this X, the set of all X that satisfies these conditions would be in an affine space of dimension n minus P. So in order to be a non-trivial optimization problem, P would be less than n. In general, P would be much less than n, right? So if that is the case, then this maximization problem is a linear program in P variables, where P is less than n, correct? So hopefully I've gained something by reducing the complexity of this problem. Instead of an n-dimensional optimization problem or an optimization problem in n variables, I've brought it down to P variables in this particular case. Okay. So let's see one particular example. Suppose my goal is to minimize. Yes. P is not necessarily less than n. Why do you say that? So suppose P was equal to n. Okay. Right? It suffices to consider P less than or equal to n. Do you agree with that point? Okay, so this after all defines some set of constraints, correct? And let's assume that this corresponds to a minimal set of constraints. Okay, if there is no solution to Ax equal to B, then there is no solution to this optimization problem at all, correct? If this has a solution, if it has like if there are multiple feasible points, then it must mean that there should be multiple solutions to this particular problem, right? Now, I agree with your point that the actual number of constraints could be larger than n, but you should be able to reduce it to fewer than n constraints because ultimately all of this depends on the rank of A, and the rank of A can only be less than or equal to n. If A is in fact full rank and A is invertible, then this would have exactly one solution. So there's nothing to solve at all. It becomes interesting only when you have infinitely many solutions, right? So let's see one example. Suppose I want to minimize x1 plus x2 subject to the constraint that maybe x1 plus 2x2 equal to 1, x1 greater than or equal to 0, and x2 is greater than or equal to 0. Okay, this is in fact in the standard form of LP that I had earlier. Okay, this is a nice simple example that we can try to solve geometrically. In fact, I mean, there are different ways you can try to solve this analytically, but also it's pretty easy to look at this geometrically. So what does the constraint set look like? x1 should be greater than or equal to 0 and x2 should be greater than or equal to 0. We say this is x1, this is x2, so it should lie in the first quadrant. And x1 plus 2x2 should be equal to 1. So basically it should lie on the following line. At what point does it intersect the x1 axis? Correct. So this is 1 comma 0, and the x2 axis? Correct. So 0 comma half. Right, and the function is x1 plus x2. So in other words, as you go along this particular direction, the function value increases. So the closer you are to the 0 vector, the lower the value of the function is. So if you had to guess, what would be the minimum value of x1 plus x2 along this particular line? Yeah.
Intersection
So I'm asking for the minimum value of x1 plus x2 on this particular line. Or if you want to simplify, yeah, 1 by 3, 1 by 3, 1 by 3, what would be the value? What would be x1 plus x2? 2 by 3. It would actually be equal to half, right? So just if it's that difficult, just substitute x1 equal to 1 minus 2x2 and plug it back here. What would you get? x1 equal to 1 minus 2x2 would imply that my original f0 of x, this would be equal to just 1 minus 2x2 plus x2, which would be 1 minus x2 plus x2. This is 1 minus x2, correct? But what values can x2 take? So x2 should be greater than or equal to 0, and it should be less than or equal to half, because this is the range over which x2 can vary, right? And what is the minimum value that this can take? It would be half, correct? So this optimization problem has a solution equal to half. That's your f star. Okay, we also have an expression for the dual problem, right? What would the dual problem be? So remember that the standard form is C transpose X. That's what you want to minimize, subject to AX equal to B and X greater than or equal to 0. So what is B equal to? It's just 1. It's a scalar, right? So nu would in fact be a single variable, right? So the dual problem would be you want to maximize minus nu times 1 subject to, what are the constraints? Lambda should be, so A transpose nu plus C should be greater than or equal to 0. What is A transpose? So it's the vector 1 comma 2 times nu. This is my A transpose, this is nu, plus C equal to plus C is greater than or equal to 0. What is C? C is just 1 comma 1 is greater than or equal to 0. But what is the constraint set reduced to? So it is nu greater than or equal to -1 and 2 nu greater than or equal to -1. Right? Which is the same as saying that nu should be greater than or equal to, these two are redundant. Right? So in fact, this contains this. So nu should be greater than or equal to -half. So the goal is to maximize minus nu, or in other words, minimize nu among all nu greater than or equal to -half. So the solution to this G star is equal to 1/2. Okay, so this is an example where strong duality holds. F star is equal to G star. So I had two optimization problems, the original problem and the dual problem, and the solution to the dual problem, or the maximum value for the dual problem, is equal to the minimum value for the primal problem. From this, it's not obvious, right? We can't really get it directly. But we can get the optimal value. Any questions? Okay. So this gives us some intuition. Well, from one optimization problem, we've gone to the other. But in the next class, we'll see how can we potentially solve the dual problem. I'll give a set of conditions, and if you're able to just check those, in other words, if you're able to solve for those conditions, then you get a solution to the minimum. Okay, and in fact, this approach will also allow you to get the x that minimizes the function. Okay, to answer your question. But this particular approach is not always guaranteed to work. It's a very general approach which you can also potentially apply to non-convex problems. But it's only in the case of convex problems that you can get some guarantees. And we'll see what those are in the next class. Okay, so let's stop here.